Shall we start, sir?
Yeah, sure.
Welcome all to the second session of the day. Over to you, sir.
Okay, so now I told you benzene hydrogens comes around 7 to 8 ppm. You see that there is also ortho meta and para hydrogens. They normally have different chemical environment around it, because you know that ortho substitution, meta and para substitution are possible depending on the type of substituent here. So in principle, that is not just one single peak at 7 to 8 ppm. It is a bunch of peaks. So this is toluene. You can see CH3 that comes at 2.2 ppm also, while these hydrogens all bunched up around 7.5, 7.2 ppm. Okay. Normally, we never try to analyze it in great detail here. Just figure out what is the intensity of this peak or the integral values of these peaks. And if it fits to 5, we say it's 5. Okay. But we can analyze if you go to a higher spectrometer frequency, very high field, like 600 or 700 megahertz. Then we should be able to analyze it more detailed, and what kind of coupling, what kind of substitution, and everything, we should be able to get it. Okay, we will come to all this intensity in a bit time. But first, the number of signals. The number of signals equals the number of different types of protons that I have already told you. So, for example, here in this ether, CH3, both of them are same because they are attached to same oxygen, and only one signal is observed. While here you get two signals, CH3, CH2, Cl, two types of H, two types of signal you should observe. And here you get three signals because CH3, CH2, CH3, they are all having different. This CH3 is different from this CH3 because this CH3 is attached to an oxygen, while this CH3 is attached to a CH2. This will be more deshielded, while this CH3 is more shielded. Okay, here both these CH2 will have the same chemical shift because they are related by a C2 axis, and they have a single chlorine and a carbon attached. Here also it is a single chlorine and a carbon attached, so they have the same chemical shift. Okay, that's because it's symmetric. Now in here you get three signals for this particular molecule. This CH2, and this CH2. All the three will have different chemical shifts. Now, if this Br was replaced with the chlorine, then you will get two signals. This CH2 and this CH2 will be the same, while this CH2 will be different. So you get two signals if the Br was replaced with the chlorine. Now, in this case, this CH3 and this CH3 will have different chemical shift. This I told you is very close to 2.1 ppm. Or CH3 will come around 3.6 ppm or so. In this ethanol molecule, you get three signals. So the intensity, now coming to the intensity, now that tells you the number of peaks, how many peaks are there. There is also coupling. I will come to that a bit. So now first the intensity of the signal. So in this ester, CH3, there is a green and pink hydrogens. You see two metals, green and pink, CH3, CH3. You have to get two signals, right? So this CH3 I told you somewhere around 2.1. So where is that? That is around here, 2.1. So this green is the CH3, while this CH3 that comes around 3.6 something, as I told you before. So that is the pink one, right? Now, what we can say about the intensity? Now, intensity, what we do is the area under the curve. Area meaning this is a signal, right? This is a signal. We integrate. That means we take the area under the curve. Area under the curve. Now, if you take the area under the curve, that is proportional to the number of absorbing protons. Okay. So you see that in the green there are three hydrogens. In the pink there is three hydrogens. So you should have an intensity ratio. It's proportional. So that means you should have the same intensity ratio, 1:1 intensity ratio, and that is what we are seeing here. Okay, and the integrals that you're going to get, integral meaning area under the curve, they should be same. Okay, they should be same. So if you take, that should be 1:1 ratio. Now, how are you going to find out? Now, let's look at this molecule. That is C9H10O2. C9H10O2. So there are totally 10 hydrogens. 10 hydrogens. You can see this, right? C9H10O2. There are 10 hydrogens in this molecule. Okay, and we are taking the proton NMR. There are 3 signals you can see: signal A, signal B, and signal C. So 3 signals, and we find the area under the curve. So this integral, you see this this way. This integral that tells you that this signal has been integrated or found the area. Now, what is that area? That is given by 54 for signal A, 23 for signal B, and 33 for signal C. Now, I told you the area under the curve is proportional to the number of absorbing hydrogens in your molecule, number of absorbing hydrogens of that signal. So, okay, so 54, 23, and 33. Now, so how do we find the number? This is not the number, right? 54, 23, and 33 are not the number. There are only 10 hydrogens, so of course these are not the number. So I said it is proportional. So how do we find the number of hydrogens here? So it's one simple way to do it, or the proper way of doing is to add up these 3. 54 plus 23 plus 33, that is 110 units. So 110 units will give you 10 hydrogens. Okay, 110 units will give you 10 hydrogens. So what is one hydrogen giving you? How many units will one hydrogen giving you? That will be somewhere around 11 units. 110 divided by 10, right? So 10 protons is giving you 110 units. The total integral value should be equal to the number of hydrogens. Okay, so you get 110 units. If you add up all of this, that gives you 10 hydrogens. Okay, so one hydrogen, how many units are there? So 11 units per hydrogen. 11 units are there. So 110 divided by 10, 11 units per hydrogen. So how many hydrogens will be there in signal A? 54 divided by 11, that is around 5. 23 divided by 11, that will be around 2. 33 divided by 11, that is 3. Right? So 5, 2, and 3. That will be total 10. Okay. So here there will be 5 hydrogens. There will be 2 hydrogens, and there will be 3 hydrogens here. This is how you calculate the number of hydrogens in the in your signal, corresponding to each signal. Okay. So let's do it. So here we have C5H12O. Okay. C5H12O. There are 2 signals. Around 1, there is 1 signal. 60 is the integral value, and 3 you will get 20 as the integral value. Now you should be able to, this corresponds, so 60 plus 20, 80 units corresponds to 12 hydrogen. So what will be 1 hydrogen corresponds to 60 divided by 12. Other than that, what are the other possible? Now 20 and 30, it is 3 times this, right? So how many, the number of hydrogens here would be 3 times this. Number of hydrogens here would be 3 times this. Now, is there a way to reach 12 doing that? 3 and 9. 3 and 9 will work, right? So if it is 3 here and 9 here, 3 here and 9 here, then it's thrice here. So 3 here and 9 here, that will be thrice here. So that is also one, just if you have a number of signals are very less, it's easy to see. This is TMS, okay? So that you don't integrate. You can do that. So here there will be 3, and this will be, so what is a molecule? This will be CS3O CCS. So you cannot have 9 valency. You cannot have 9 hydrogens attached to a single carbon, right? That cannot be, right? So you can only maximum have 4 valency for carbon, right? So you have to have CS3 thrice. CS3 thrice will have 9 hydrogens, which has equivalent, They have the same chemical shift, right? Because all these 9 hydrogens here is attached to a carbon, which is attached to another carbon, which is attached to an oxygen. While this methyl, however, is attached directly to an oxygen. So that comes greater than 3 ppm, this is more shielded and this is more deshielded. Okay, CS3O, CS3, CCS3 thrice. That satisfies the 5 also. 1, 2, 3 carbons here. So that is 5H12O, single oxygen. Another thing, C6H12O2. Okay, C6H12O2. Again, you see TMS peak. Do not integrate the TMS peak. You integrate the pink one, you integrate the green one. So there are 2 signals, 6 and 18. Again, you see that the 18, the signal at 1.2 ppm, that is thrice this. That is thrice this. Okay, so if it is H12, so it is again has to be 3 and 9, because that is the only way you can get to 12. 3 and 9 is the only way you can get to 12, and is proportional to these intensities or these integral values that I've shown you. Okay, so 3. So this has to be 3, and this has to be 9. Otherwise, what you have to do, you just have to multiply 18 plus 6, 24 units corresponds to 12 hydrogens. So what will be 1 unit corresponds to? 1 hydrogen corresponds to, that will be 3 units. So 24 divided by 2 units, right? So 6 by 2, this will be 3, and 18 by 2, that will be 9. Okay. There is a disturbance coming in. Okay. Now, what will be the structure of this molecule? This is also very similar, but you have 2 oxygen now. Okay, you have 2 oxygen, so you have to worry about that. And also the chemical shift. This is quite deshielded, while this is quite deshielded, while this is shielded. Okay, so this is probably attached to oxygen. Oxygen. This is not attached to an oxygen. You see this CH3 starts in C double bond O CH3. Okay, so this is the only way you can get to this one. Now we come to something called, again, this is also has to do with the number of signals. It's called the splitting of signals. Okay, splitting of signals, or the coupling between the nuclei. Okay, the spectra up to this point has been limited to a single absorption called singlet. Okay, singlet. That is what we have seen here. This is a singlet. This is a singlet. We say 1.1 singlet peak, 3.8 singlet peak. Okay. Now you see that here. You see in this particular. This is bromo propane. There is a dibromopropane. So a tribromoethane. Sorry. It's dibromo. No, tribromo. Okay, so you see that this hydrogen, for example, is attached to 2 bromine atoms. So this will be highly deshielded compared to this CH2, for example. Okay, so here this would be this CH2 and this would be this CH. But you see that is not a single peak. This signal, this CH2 is a doublet. You see 2 peaks coming to it. You get 2 peaks, 2 peaks. It's a doublet. Okay, 2 peaks meaning doublet. This hydrogen, that is the deshielded, because there are 2 bromine attached to it, that is coming around 5.8 ppm. That is a triplet. You see 1, 2, 3 peaks there. So rather than seeing a single peak, you have 3 peaks. And this, you to zoom it, you see the pattern also like this. This is the triplet. Okay, triplet peak, and this is a doublet peak. Okay, so why do they come? That is because of splitting or coupling between the hydrogens. This hydrogen coupled to this hydrogen. Of course, they vice versa. So these hydrogens will be coupled to this. This hydrogen will be coupled to these hydrogens. Okay, since they coupled, what do you mean by coupling? A coupling, and any coupling, it doesn't have to be NMR coupling. Any coupling is that the energy of whatever that we are observing is depending on the energy of the coupled partner. Okay, energy of the coupled partner. That is what coupling is. Okay, so energy of your energy or the spin states of this hydrogen is influenced by the spin states of the methylene hydrogens here. Similarly, the spin states of these methylene hydrogens is influenced by the spin states of this CH hydrogen. Okay, so how does it arise? This mainly arises because of this. So, for example, you are applying a magnetic field, B0 field. Now, if the other guy, the coupled partner, is on the same direction, that means if it is upstate, that is going to influence. That is giving you more favorable line width. So it is going to reduce your energy value. But if the other coupled partner spin state is -half, okay, -half, that is going to oppose your applied magnetic field. The magnetic field created by it is going to oppose your magnetic field of B0 is being opposed by your applied the coupled partner. So you will have a different frequency because your magnetic field experienced by that nucleus is going to be different, right? So no adjacent carbon atom, no adjacent hydrogen atom, you field only B0 and the chemical shielding and everything, and you get a single peak. But if you have adjacent hydrogen atom, then this particular hydrogen atom will field two different fields. One where you see where its own field is being enhanced by the a coupled partner or decreased by the coupled partner, because they have different spin states, plus half and minus half state. Okay, and that is why you get a splitting like that. And the ratio would be 1:1. The ratio would be 1:1. Now, normally this coupling is through bond. Now, how does that work? Now, your nucleus here. Let's say you have let's say you have CH-A-B. Okay. Now we are looking at hydrogen atom. Okay, and that is why it is splitting like this. This splitting. Now it is being coupled. This hydrogen atom is being coupled. This hydrogen HA is being coupled with this HB. Now, how does this coupling works? This energy here depends on the polarizability of, or the electron density, or the valence electrons of the bonding electrons of this CH bond, which then influences this CC bond, the electron spin states of this CC bond, which is then influence the spin state of this CH bond electrons, which then polarizes the HB. Okay, so HA and HB. So HB's spin state, so vice versa also. The HB spin state is being transmitted to HA. HB spin state is being so the energy of HA is getting influenced by the HB spin state. Okay, so HB can polarize this guy. This will polarize, meaning that will do the opposite, and then this will go to opposite of this. This will then do the opposite, which then influences the HA. So H and HB are coupled to each other. This is why it's called a through bond coupling. Okay, through bond or scalar coupling, or we call the J coupling. J coupling. It's also called scalar coupling. Okay, or through bond coupling. Okay, now I'll tell you this. So this is signal of interest. This is signal of interest when there is no coupled partner attached to it. Okay, there is no coupled one. There is no, you don't have any adjacent hydrogen atom attached to it. Now, if you have one neighboring nuclear spin, what happens? There is two spin state possible, either up or down. Either up or down. Like you name it, this one. So what happens? Because of this up, because being up, you get a signal that is being shifted. So if signal of interest, if there was no coupling, then it will come exactly at this O frequency. Now, because of this up state, it has been shifted to a higher frequency level this year. Now, if it is, if you have down, then it is getting shifted in the negative direction. Okay. Now, this difference between these two signals, this doublet, is J hertz, which is called J hertz. We give it in J hertz, and this is independent of the magnetic field. It is independent of the magnetic field. This is always given. Coupling is always given in hertz, and that is independent of magnetic field. So in 60 megahertz, if it says 2 hertz coupling between the doublet, it is 2 hertz even at 600 megahertz. Okay, it will not change. Okay, it will not change. It will be 2 hertz in 600 megahertz also. And the intensity range, you see that when there is no coupling, the intensity is really high. When it is coupling, this intensity, when there was no coupling, the intensity is high. When you have the splitting, it has reduced to half. Okay, but then it will have the same intensity. The coupled peaks have the same intensity, or we call 1:1 splitting. It is 1:1 splitting. Now the intensity has reduced, but the intensity of the coupled partners are same. The coupled signals are the same, 1:1 splitting for a one neighboring nuclear spin. If you have two neighboring nuclear spin with same chemical shift, this is how it goes. Your signal of interest, if it is not there, if there is no coupling partner, the frequency will be at 0 frequency. Now there are now four possible states. Now in the first, this I denote the two neighboring partners. One is in purple, the other one is in green. Okay, so both of the neighbors are in the up state. That is one possible orientation. Now both of the neighboring partners will be in the minus half states or down state, minus half states. So this is denoted like that. Okay, these are MS values, right? MS values, minus half states. Okay, then there are two more possibilities. One is the first one is down and the second one is up. The first one is up and the second one is down. Okay, but these two have equal energy. They have equal energy, while this and this will have different energy. This and this will have different energy because both of them they will both enhance the magnetic field. These two will be down because both will decrease the magnetic field, while these two has almost zero thing. So what happens to the intensity, however, you get like this. This will be, this and this will have equal intensity. This and this will be equal because there is only one way to reach these two possibilities. While these two, there are two possibilities. So this will be twice this, right? This one will be twice of these two guys. Okay, so what is the intensity ratio? And the Hertz value is, this is the Hertz value. Okay, not from here to here, that will be 2 J Hertz, but from here to outer to middle, that will be the J Hertz. Okay, and it will be 1:2:1 splitting. Total intensity, if you add up all the total intensity, it should match this intensity. Okay, so when you integrate a signal, you have to integrate over the multiplet in order to get the whole 3 multiplet. If this is coming from the same signal, same chemical shift, you have to integrate over the entire multiplet in order to get actually proportional hydrogens. Okay, otherwise you will miss certain multiplet, then you won't get the actual value. All right, so if you add up all the intensity, it will match the original one. Okay, so that is how it works. So 1:2:1 splitting is what we observe in NMR. Likewise, you can continuously do. So the intensity pattern follows like that. So first one, you have 1, then you have 2. If it is alone, then it is 1. If you have a 1 spin coupled, then you have 1:1 intensity. If you have 2 spin coupled, then it becomes 1:1. If you have 3 spin coupled, it becomes 1:3:1. Okay, so you see it is a Pascal's triangle. Okay, now normally the number of signal, the splitting, you see 3 signals here, right? 3 signals here, 2 signals here, is given by n+1 for protons, or generally it is 2ni+1, where I is the spin of coupled partner. Okay, since I is half for the hydrogens, if it is only hydrogens that is coupling to each other, if I is half, sorry, I is half here, I is half, then it drops to the original n+1 rule for the protons. Okay, n+1 rule for the protons. That means n is the number of neighboring. So here n is the number of this is the number of neighboring coupled partner. Sorry, n is the number of coupled partner. So n is the number of coupled partner. So here you have a single coupled partner. So n+1 2. For here you had 3. You have 2 coupled partner. Hence the number is 2 + 1 3. Okay, here you have here you have n is equal to 2 because you have 2 neighboring coupled partners. So you n+1 3 peaks. You have to say. If you have 3 coupled partner, you will get 4 peaks, and the intensity ratio is 1:3:3:1, and it follows the Pascal's triangle. Okay, I hope that is clear. So this is what I said, 1:3:3:1. You can see the spin states. Here there is only one way of applying 3 of them on the up and one way to apply 3, but there are 3 ways of doing 2 up and 1 down, and 1 up and 2 down and 1 up. So 1:3:3:1. They all have different energies. Yeah, this I have already told you. At 100 megahertz, if the splitting is 7.5 hertz, it is the same 7.5 hertz. You go into 200 megahertz. At 200, again, some thing is coming. 200 megahertz also, the J coupling is still the same, 7.5 hertz. Okay, so it is independent. The J coupling in hertz is independent of field. Independent of field. Now there are notations for this. Now I just drawn that. If you have a 3J coupling, why is it called a 3J coupling? Here there is 1 bond here, 1 bond here, and so 1, 2, 3. 3. This is a 3J. This is this H and these 2 H's are coupled to each other through a 3J coupling. Okay, 3J coupling. 1 bond here, 2nd bond, 3rd bond. 3J coupling. This is called the vicinal coupling, otherwise called the vicinal coupling. Vicinal coupling, and this is the most common coupling that we see. Vicinal coupling. There is also geminal coupling. It's a 2J coupling, like here. This is 2J coupling. Most of the cases, these hydrogens have the same chemical shift. Then hence they don't couple to each other. But many times, if you have sometimes if you have like this is a geminal. These don't have the same chemical shift, but this is a geminal coupling. They couple to each other. Because why is that? Because this hydrogen is cis to chlorine and this hydrogen is trans to CH3, while this hydrogen is cis to CH3 and trans to chlorine. So they have a different chemical environment. So and these 2 hydrogens couple to each other. Okay, so this is a geminal coupling that is possible, but many often cases that like CH2 in any CH2 things and all, they normally come close to other. Otherwise, it has to be diastereotopic. Diastereotopic is another thing. There is anisotropic, diastereotopic, and homotopic. Homotopic is when all hydrogens are equal. They are related to each other by symmetry, any C2 axis or something like that. But diastereotopic is something where you have already a chiral center in your molecule. Then these hydrogens then becomes diastereo. They are if any substitutions happen in these hydrogens, then that becomes a diastereomer, right? A diastereomer. So these hydrogens have a spatial interaction that is kind of different. Okay, hence their chemical shift will not be actually same. Okay, it's very close but will not be same. Okay, so they then can couple with each other. Now I probably missed this thing. I told you they can couple. These hydrogens can couple only if they are different chemical shift. They are not equivalent. They are not equivalent. They couple only when they are equivalent. If they are equivalent like here, then they don't couple. Here they are not equivalent. Here they are not equivalent, hence they couple. They are not equivalent, hence they couple. If they are equivalent, then the coupling is 0. They don't couple with each other. Okay, equivalent meaning they have the same chemical shift, almost same chemical shift. Okay, some of the coupling constants I'll give you. So for example, vicinal coupling goes from 6 to 8. This is the most common, I told you, 6 to 8 hertz. This is a trans thing, and this is really important. This will help trans and cis. The trans has a higher coupling constant compared to cis. It's about 10, and this will be below 10 most likely. There it goes 15 hertz and all, but generally it is close to 10, while this is quite above 10. Okay, so generally trans coupling is higher compared to cis coupling. Okay, so this will help you distinguishing trans and cis isomers in your compound. Okay, now also another important thing is in the cyclohexane things, you can see that in equatorial, the axial is quite large compared to axial equatorial or equatorial. Okay, so axial coupling, like for example, here, this axial coupling, that will be higher, more than 10 hertz compared to axial equatorial or equatorial coupling. All right, so that is quite important. This geminal coupling is 0 to 5 Hertz, very close to, it's less than even the vicinal hydrogens. The main problem is they are kind of close to in chemical shift also. Okay, so the trans hydrogen trans coupling is higher compared to cis coupling. Axial coupling is higher compared to equatorial or axial equatorial coupling. Okay, so with this you should be able to determine geometry of your molecule also, right? So for example, this is a distinguishing cis and trans. This is for chloropropionic acid. You see that this HA and HB are trans to each other, right? They will have different chemical shift, of course, HA and HB, and you see it's a doublet of a doublet. The cis also, the cis also shows a doublet of a doublet. Now, how do you distinguish between these two guys and almost similar chemical shifts, right? So how do you distinguish this one? Trans coupling is 14 Hertz, while cis coupling is 8 Hertz. Okay, so when you measure the coupling, if it is higher, trans coupling is higher, then that means that it is a trans. If the coupling is smaller, less than 10 Hertz, then it is clearly cis. Okay, so this is chloropropionic acid, 3-chloropropionic acid, propenionic acid, and that is able to be distinguished whether it is cis or trans by doing just measuring the coupling constants. There is also a way of determining the dihedral angle of your molecule. It's through Martin-Karplus relationship. I don't have to write the relationship, but this is the graph of that relationship. This is a quadratic equation in cos thetas and all, but the graph of this equation. So what you do normally is find that this angle, this is dihedral angle, and this is the coupling. So this is angle, this is the coupling constant in Hertz. Okay, you see that if the Hertz, if the coupling is somewhere around this above or close to 10 or above 10, then that is around 180 degree. Okay, dihedral angle is 180 degree. That means this has gone all the way up here. Okay, this theta has gone all the way up here. That is a 180 degree. That is dihedral angle. This theta is what I'm talking about. Okay, this is a Newman projection. Okay, and that will be all the way here. If it is very close to 2 or 0, then it means it's somewhere around 90 or something. Okay, and if it is anywhere between 6 and 0 or 6 or 2 or something like that, it will be less than 90. Okay, like that it goes on. It could be the other side also. That is also possible. But what is able to distinguish, for example, here in this particular molecule, you see that the alpha comes up to 65. Just looking at the coupling, you just take the 4 Hertz, put the 4 Hertz, and find out where the coupling is. Okay, 4 Hertz, that will be somewhere around 65, right? So, but look at this coupling, this HA, that is around 12 Hertz. At 12 Hertz, where is the 12 Hertz? That is somewhere here. That will be 180. It says 175 degree. Okay, so that's how much you can get from the. This is an empirical formula. There is no derivation for this formula. Martin-Karplus got Nobel Prize not for this. He did it for molecular dynamics, but he still worked on NMR. He had worked on NMR. He started with NMR. All right. So this is very important aspect in biomolecules also. So we determine dihedral angles, we find chemical shifts and coupling constants, and then determine dihedral angles of your peptide backbone. And that should be able to distinguish between alpha helix, beta sheets, and things like that. They have different dihedral angles. Now, if you want to do NMR determining structure of molecules, what is important is to do this. Normally, what in colleges, for the students at least, they give you a atomic formula, and you have to find out the molecular structure of it. So, what they gives in carbon this many, hydrogen this many, nitrogen this many, oxygen this many. Okay, and we have to find out the structure using NMR, IR, and things like that. So, the first thing that one should do is to find the number of rings plus the pi bond, double bonds in your sample. That is equal to number of carbons minus the number of hydrogen divided by 2 minus number of halogens divided by 2 plus number of nitrogen divided by 2 plus 1. Okay, if nitrogen is not there, eliminate this. Chlorine is not there. If halogens are not there, eliminate this. But this +1 cannot be eliminated. Okay, so C minus H over 2 minus X over 2 plus N over 2 plus 1. Okay, this is the formula. That gives you the number of rings plus pi bonds. Okay, here are a few problems one can do, and that also has coupling. Okay, so here's one formula: C2H3 Br3, C2H3 Br3, and you can see one is kind of shifted out. So you have 2 minus 6 divided by 2, so 3 plus 1, so you basically have 0. So 0 unsaturation or double bond of pi rings. Okay, 0 unsaturation. Using this formula, you should be able to get that this has 0 unsaturation. Right, so you have two peaks, one at 4.1 ppm and another one at 5.7 ppm. Okay, 5.7. This here at 4.1 ppm is a doublet and this is a triplet. So what does this tell you? This tells you that this guy here has an attached CH. Okay, it has an attached CH, because that has made it doublet. What does this tells you? This tells you that it has an attached CH2. That is sufficient, right? It doesn't have the intensity, integral, but this is more than sufficient. This is CH2 and this is, this has an attached CH2 and this has an attached CH. Now what happens? So this has to be a CH. This has to be a CH attached to some bromine, some 2 bromines or something like that, because it has gone down so much lower in higher in ppm values. So it is kind of quite deshielded. While this has to be a CH2. Okay, it came off. So you see that this CH2, this CH2 is what we see here. This has an attached CH, so that is this CHA, that is here, which is this HA is attached to a CH2. That is what I said here. This has an attached CH2, so it has a CH2. So this has 2 bromine, that is why it has quite deshielded compared to, or quite downfield shifted compared to the this CH2, which is a single bromine attached to it. All right. Now we go into this C8H10. C8H10, and it has also integral values. Now you see there is an integral value at between 7 and 8, and has an integral of 5. Okay, 5. So what is that? That has to be a benzene ring, a monosubstituted benzene ring. If it is disubstituted, then the integral value will be 4. If it is monosubstituted, there are 5 hydrogens, right? There's no 6 hydrogens because it's monosubstituted. So 5 hydrogens. So that is 5. This is an integral. So if you add up these integrals, it should come to 5. So 5 plus 2 plus 3 and 10, right? So that is fine. So you don't have to now calculate how many hydrogens are between. So it is already done. 5, 2, and 3. So this is 5. So that is a monosubstituted benzene ring. And I already told you benzene comes around 7 to 8. So this is benzene ring. Now 2 to 3, there is something that is a quadrate. That means there are 4 peaks. That means it is attached to this particular spin or this particular resonance. A peak is attached to a CH3. It's attached to, it is coupled to a CH3. It is coupled to a CH3. While here, this 1.2 ppm or something, there is a triplet. That means this guy is attached to a CH2. And from here, these two integral values, it is easy to see, right? This has to be a CH3. And this has to be a CH2, and this has to be attached to each other. So it has to be a CH2, CH3, because only then it makes sense. 3, 2, 5. Now what will be the benzene ring? So this is what it will be, right? That is what C2H5 benzene. Now this is a little more complicated. C5H10O. C5H10O. Can you figure out what is the unsaturation? Unsaturation would be 5 minus 5 plus 1. That would be 1 unsaturation compound. Right? This is 10 divided by 2 plus 1. Okay. You don't have to worry about the oxygen. That should not be there. So it has 1 unsaturation. Okay. Now, one thing that you see here is that there is a 2.1 ppm, A, B, and C. There are three peaks here, A, B, and C. The B peak is a doublet, while C peak is a complicated multiplet. It's a complicated multiplet. Okay. So how are you going to find? And also the integral. Integral here is 1, 3, and 6 here. 1, 3, and 6 here. Now, how do you get 6? It can be CS3 thrice. CS3 twice. This is CS3, which doesn't have any coupled partner. Which doesn't have any coupled partner. There is one way of doing it. As you also know that there is an oxygen, so you have a C double bond or CS3. I told you 2.1 ppm. A CS3 attached to a carbonyl can come at 2.1 ppm. Okay, so CS3. It doesn't have a coupling partner, so it has to attach to a quaternary carbon. Okay, so that is possible. Then what else is possible now? There is single peak here and a 6 peak here. This is what we have. We have CH, CS3, CS3. Now, what does it gives you? This CH3, this CH is coupled to 6 hydrogens, CS3 and CS3. These two CH3s have the same chemical shape because they are both symmetric and they are attached to CH. Okay, so these 6 hydrogens are coupled to this hydrogen. So this H is going to make is split into a heptet, 7 peaks. Can you see that? 1, 2, 3, 4, 5, 6, 7 peaks. 7 peaks. The intensity ratio, you have to do the Pascal's triangle to find the intensity ratio. The 7 peaks. Now, normally you don't get this if you. These lines are very close to noise. Now, this hydrogen will be split to 7. While these hydrogens, these are 6 hydrogens of them, they are now split because of this H into a doublet, because the neighbor is only 1, so it will be split as a doublet, and that is why it is a doublet here. So these 6 hydrogens are from here, and that is a doublet. You see a doublet, while this CH is a heptet, 7 peaks. Now, how do you know that these two guys are coupled to each other? You measure the coupling constant. You measure the coupling constant here and coupling constant here, and they have to be same. They have to be same because this is coupled to this is coupled to this. They are, so the same coupling constant has to exist here as well as here. Okay, so they have to be coupled to each other and they have to have the same coupling constant. While this guy is not coupled, that is why this becomes here. Okay, so this is what we see. Now this is C7, H7, NO2. You get again 3 peaks. And you see there are 7 hydrogens, so you see that 2 here, 2 here, and 3 here. So the ratio, this is 2 plus 2, 4 plus 3, 7. That is fine. Then there's a nitrogen and there is a oxygen. Okay, there are 2 oxygens that is coming up. I will not do the thing because that will be more problem. What you can see, this is an example to give you the difference in chemical shift that you see in the aromatic. So you see already that it is between 7 and 8. That means it can be an aromatic system. So if you do the unsaturation, the number of pi rings, number of rings plus the pi bonds, we see that it is 7 minus 7. Is it 7? Yeah, 7 by 2 plus 1 by 2 plus 1. Okay. So this is 7 minus 4 plus 1. So that is 4. There are 4 unsaturation. There is 4 unsaturation, and that is taken care here, right? You have the ring, that will be 1 unsaturation, so because of the benzene ring, and you have 3 double bonds. 3 double bonds. So 3 plus 1, 4 double bond. Then you have the NO2. Now the question is, what is the substitution for this benzene ring? Now there are 4 of them. That means it has to be double substituted. If it was 5, because the the integral is 4, 2 here and 2 here, so that's 4. If it was 5, then it is monosubstituted. If it is 4, it is disubstituted. So it is disubstituted. Okay, and then you have CS3. So you know where CS3 is going to come, and then you have only the NO2 because that is not part of the unsaturation part. So you will get this O2 NO2 and like that. It has to be also symmetric because it looks quite symmetric. Okay, this hydrogens, this doublet. If it was like a meta or something like that, there will be more coupling partners involved. So that means ortho para, ortho para. All of this gets coupled to each other. All the hydrogens coupled to each other. Here there are only 2 types of chemical shifts: HA and HB. HA and HB. So that is the 2 types of chemical shift, and there seems to be a doublet mostly. That is because the HB is coupled to HA, HA is coupled to HB, and they should have similar hertz. I mean, the coupling constant. 8 hertz is written here, so they have the same coupling constant. Now, C3H6Cl2. In order to be fast, I'm just doing everything together with the formula. Otherwise, we have to do it in a separate way. So these 2 hydrogens, for example, they have so if you look at it, you see that they seems to be have the same chemical because these 2 hydrogens are attached to a chlorine, right? Now both of them seems to have the same chemical shift, but actually it is not. Why is it? Because this carbon here is a stereocenter. This carbon is a stereocenter. So hence these 2 hydrogens are diastereotopic. That is, they are going to be, if you replace this H with a D, you will get a diastereomer. You replace this H with a D, you will get a different diastereomer. Okay, different diastereomer. So these are diastereotopic, and the diastereotopic protons have different chemical shifts. So they have different chemical shifts, and they couple with each other because they have different chemical shifts. They couple with each other. Okay, so these 2 hydrogens have different coupling. So in principle, that is what you observe. And this CS3, of course, is here, and that is a doublet because of this hydrogen. That is a doublet because of this hydrogen that is coupled to this hydrogen. So what about this? This hydrogen is coupled to this CS3 and is coupled to this guy as well as this guy. You see, this hydrogen is coupled to this CS3. It is also coupled to this hydrogen and this hydrogen. Okay, so what will be? It will be a quadret of a doublet of a doublet. You get a whole problem. While how about these 2 hydrogens? This hydrogen is a doublet of a doublet. It's a doublet of a doublet. This hydrogen will not couple to this because it is more than 3J. Okay. Normally, what happens if you go higher in the as you go along the bond, if the number of bond increases between 2 coupled partner, the coupling drops to 0. Okay. So 3J is up to what we see, except for in case of aromatic compounds, which can show 4J coupling. But normally, it is 3J coupling is what we actually see. So this hydrogen can couple to this hydrogen and this hydrogen. So it is a doublet of a doublet. The coupling constant between these 2 and these 2 will be different because they are different, right? So they are going to be, so it's a doublet of a doublet. It's not going to be a triplet. It is going to be a doublet of a doublet. That means it will give you 4 peaks rather than 3 peaks. Okay. So it's a doublet of this hydrogen also similarly. It will couple to this guy and this guy. Okay. And that will be a doublet of a doublet. Okay. So how about this? This will be a doublet. This will be doublet of a doublet. This will be more multiplet. You can then add up 3 plus 2 is 5 plus 1 6. So n plus 1 6. So 6 coupling because there's too much of coupling. Otherwise, what happens? This is a doublet of a doublet, then the quadruplet on top of it. Okay, so which is quite difficult to actually see. Okay, so that is why this is all doubled up here out here. But you can see it's a doublet of a doublet is clearly visible. The intensity ratio, if it was it's a triplet, then it is 1:2:1. But doublet of a doublet, these 2 guys are equal intensity. These 2 guys are equal intensity. If it is 4 lines, then it should be 1:3:3:1. That is also not the intensity ratio. So that is how you differentiate doublet of a doublet. Okay, based on the intensity ratio. So you see that it's a doublet of a doublet and is also a doublet of a doublet. And this will be a doublet. Right. So what I want to, these H's are going to be diastereotopic. diastereotopic. So enantiotopic, they will have same chemical shift in achiral environment. Diastereotopic will have different chemical shift in achiral environment. Enantiotopic will have different chemical shift in chiral environment. Chiral solvent, if you put it in a chiral solvent, enantiotopic topic hydrogens will have different chemical shift. But if you have achiral, normally that is a solvent that you use, achiral solvents, then they have the same chemical shift for enantiotopic protons. For diastereotopic, as is the case here, they will have different chemical environment, be it in chiral or achiral medium. Okay. Now we come to carbon-13 NMR. Okay, carbon-13 NMR. This is I think acetic acid. You see, carbon has this thing. Okay, I have to be fast. So carbon, as I told you, the magnetic moment depends on the gyromagnetic ratio. Now, carbon-12, I told you, is 12C, the spin is 0. So there is no NMR possible. 13C, the spin is half. Okay, so it is possible. But the problem is 13C is only 1% of the whole carbon. So if you have 100 molecule of carbon, of CH4, only 1% of it, one of the carbon, methane, will be labeled with a carbon-13. Okay, so 100 molecules of methane, out of 100 molecule, one molecule of methane, one methane molecule will have carbon-13 as their carbon environment. So the sensitivity is going to drop down relatively. Also, the gyromagnetic ratio of carbon-13 is 1/4 of carbon hydrogen. Okay, so gyromagnetic ratio is also very small. So your sensitivity M0 is really going to be small, hence the sensitivity is going to be even it's worse than, is very much worse than proton or hydrogen NMR. Okay, so but still one can do it. So here is an experiment, CH3COOH. So it's this is acetic acid, and you see that there are two carbon, CH3 and C, and you see the methyl carbon comes at around 20 ppm. The carboxyl carbon comes at around 178 ppm. Okay, 178 ppm. Okay, so you can differentiate the carbon very clearly from here. You see, this is a single peak, and this is also single peak. I'll come to that single peak. So C13 has spin half. Natural abundance is only 1.08%. The magnetic moment is also therefore small. So C13 signal is 600 times weaker than 1H. 6,000, also not 600, 6,000 times weaker than 1H. But we still measure it. We can measure it. If you measure a proton in 3 minutes, you have to take at least 45 minutes to measure a carbon-13 NMR. Okay, and you have to have good amount of carbon material in your sample in order to measure. So the chemical shift range is also different. It goes from 0 to 200 ppm. 200 ppm, 0 to 200, actually more than 200, 220 ppm and all. It's possible. Ketones and all come there. So 0 to 200 ppm. Okay. If you can use the same magnetic field in order to measure. So 1.41 Tesla, the proton magnetic, the resonance frequency is 60 megahertz, while carbon will be 15.1, divided by 4, that's all. Divided by 4, because gamma is divided by 4, 15 megahertz. 100 megahertz, it will be 25 megahertz. At 2.35 Tesla, it's 100 megahertz for the proton and 25 megahertz for the carbon. 7.05 Tesla, it's 300 megahertz for proton and 75 megahertz for carbon-13. Okay, so you can use the same magnetic field, but have different frequency, that's all. Okay, it's like going into, you have the same radio, but you can tune to 93.5 FM and one Anandapuri FM, which is around 108 or something like that, right? So that is possible. Same way, you can tune to 60 megahertz as well as you can tune to 15 megahertz. Normally, you don't see a 13C coupling, because why? Because you have 1%. 1% is the natural abundance. So in order to have the second guy to be also carbon-13, then only they can couple to each other, right? Then that means 1% of the 1%. Okay, 1% of the 1%, which is very difficult. That is absolutely You have to be really lucky. You have to measure for days in order to get a 13C, 13C. You have a huge amount of. So not probable. It's very difficult to see 13C. But 13C 1H coupling is there. It's very common. It's there. It's right there because the charomagnetic ratio of the hydrogen is abundant. CH aliphatic carbons, hydrogens, unless you have a quaternary carbon, every carbon is attached to a hydrogen. So that is possible. So you have that. That is very common. Now what happens if you have a 13C attached to a 3 hydrogen? You get a just like you have n+1 4. So you have 4 peaks. Which 1:3:3 1 in this one. If you have CH2, then you have a triplet. You have a CH, you get a doublet, and that's all. If you have no coupling, no hydrogen, then you get a singlet. Okay. However, that will be very bad. So let's look at this molecule. This is again an ester, and you see how many carbons are there. There are 6 carbons here, 6, 7, 8, 9, 10. 10 carbons here, and you see such a huge peak. More than 10 peaks, definitely, right? Now, this is not what we intended. Why is it? Because these hydrogens are coupled to carbon, giving you these multiplet patterns. That is that, and it's very difficult to figure out this multiplet pattern because the coupling constants are quite high, 140. We were in the proton-proton coupling, we were dealing with in few hertz, right? 10 hertz, 15 hertz maximum. Right here, we are talking about 140, 280 hertz and things like that. CH coupling. Okay, so these are quite high and they overlap with each other. So it is very difficult to interpret them properly. So what we do normally is to decouple the spectra. What we do is decouple the spectra. So when we are observing carbon-13, we apply a radio frequency such that the spin states of these protons are flipped. So plus half becomes minus half becomes plus half. So the carbon-13 doesn't know whether it is in plus half or whether it is attached to a plus half proton or a minus half proton. Okay, so what does carbon-13 do? There is what does this radio frequency pulsing do? It basically decouples. It is a way of decoupling the proton with the carbon with the proton. Sorry. Yeah? So when you're observing carbon, then that means when you're putting an RF frequency on carbon, on the frequency of carbon, and making the carbon come to the XY plane, you apply a 180-degree pulses on the proton channel. On the proton channel, do 180-degree. So plus half becomes minus half becomes plus half. Like that, it keeps on doing. Carbon-13 doesn't know whether the proton is in the plus half or minus half because it keeps changing each other. So I said, I'm confused. I will stay in my chemical shift position, not get shifted by the coupling constant. Okay, so that is what we have. So it gets decoupled. So what we get, this was the coupled spectra of carbon-13. When you decouple, you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, something, 10 kind of peaks turns out. This I can't differentiate. So you get the same. It's much more cleaner. You can clearly see it's much more cleaner. And this is the normal way of measuring. A decoupled carbon-13 spectra is what we normally measure. We don't actually do this. Okay, decoupled carbon-13 spectra is what we normally do. Okay. What happened to this? So how do we then get information about the multiplicity? Because multiplicity will tell you. Multiplicity, you probably should have realized in CH and when we are talking about the coupling, that the multiplicity tells you what is it attached to. No, it gives you the connectivity information. It gives you the connectivity. What is it attached to it? So CH, if it is if that particular hydrogen is a doublet, that means that CH is attached to another CH. If that CH is a triplet, that means that CH is attached to a CH2 group, like that. So it gives you the connectivity of the connectivity information. So that information is lost when you do this decoupling business. Okay, when you do the decoupling business, that information is lost. So how do you get back that information? That is to do something called DEPT, distortionless polarization, enhanced by polarization transfer. Now, DEPT experiment is a multi-pulse experiment NMR, where the quaternary carbon atom, that is able to, you have to do either DEPT 90 or DEPT 135 in order to find the information that we are looking at, whether it is methene, that is only a single H, methylene, which is 2 hydrogens attached to it, or methyl, which is 3 hydrogens attached to it, right? So how do we do that? If it is a quaternary carbon, a normal carbon-13 NMR will give you that carbon, okay? Depth will not give any quaternary carbon. Depth will not give you any quaternary carbon, okay? So you don't get a signal in the depth experiment, either depth 90 or depth 135. Now, where do you get depth 90 and depth 135? It is, as I do, a multi-pulse experiment. It's not single pulse, it's multi-pulse NMR experiment, there where you transfer the magnetization from the hydrogen to the carbon-13, okay? This depth 90 depends on the last pulse, whether it is a 90-degree pulse or a 135 pulse, that is able to edit whether it is methylene or methane and things like that. Now, depth methane, METHIN, with a single hydrogen, that gives, of course, normal carbon-13, everyone will give you signal, but depth 90 and depth 135 will not give a quaternary carbon. Okay, so methane, that will give you a positive signal both for depth 90 and depth 135. Depth 90 and depth 135, the CH carbon will give a positive signal, give you a positive signal. CH2, on the other hand, will not give any signal for depth 90. Okay, will not give any signal for depth 90, but for depth 135, it gives you a negative signal. It gives you a negative signal. Methyl CH3 will also not give any signal in the depth 90, but gives you a positive signal in the depth 135. In depth 135, it gives you a positive signal. So what do you have to do? You have to measure depth 90 and depth 135. Now, why you need to measure both of them together is very simple. If you have positive signal in depth, you just measure only depth 135, what happens? You get a positive signal. Now, it can be depth, it can be methane, it can be also methyl. Okay, so how do you differentiate methane and methyl carbon? You go and do depth 90. In that, if you still see a signal, that means it will be CH. It is not CH3. If you don't, so that is how you measure. But if you, in the depth 135 itself, you get a negative signal, then it's very clear. It's only a CH2. It is only a CH2. That is how you differentiate methyl, methylene, and methane. Okay, so you have in the depth 90 only methane will show up. Depth 135, you get both methane and methyl having positive signal, while methylene will give you a negative signal. Okay, so it's easy to find from here. So you have the CH has an intensity as sine theta. Okay, CH has an intensity sine theta. So sine 90 would be sine 90 will be 1, so you get a good signal there, right? And there is no cos, so you don't have to worry. Cos 90 is 0. So you see that cos 90 here, in both cases, cos 90, this will make the depth 90 CH2 and CH3 going to 0, while sine theta will be anywhere positive. Okay, so here cos squared theta will be giving you this CH2 is 2 sine theta cos theta. That means the cos theta above 90, it will be negative. So that is why you get a negative signal. While methyl is at cos squared theta. That means you are going to add. So it's very easy to remember also. I is sine theta. For CH2, you add a cos theta to it. So cos theta. For CH3, you add one more cos theta to it. So cos squared theta. Okay. And then you add 1, 2, 3, the ratio because of the. Carbon-13 chemical shift is very similar, just like you have de-shielding and I mean the range, of course, is from 0 to 200 and above ppm, but the behavior is very similar. So going to lower ppm value meaning more shielding, going to higher ppm value means more de-shielding. Aromatic regions comes around 120 ppm. The carbonyl carbon comes around 200 ppm. The aliphatic regions comes very close to 50 to 30 ppm. It's some 20 to 30 ppm, and even lower. The OH, the electronegative atom, when it goes somewhere around above 60, 70, 80, 90 ppm, like that. Okay, I think I stopped here. If you have, I'll just, in 5 minutes, I'll just talk about biological NMR, if it is fine with you.
Okay, sir. Okay, sir.
Okay. Now, when we do NMR, oh, actually, it was two-dimensional NMR, but I didn't want to. Okay, when we do NMR, you see that if you have biological proteins and all, the number of signals is very large. It's very difficult to do, understand, measure couplings, figure out chemical shifts and everything. So we have to do multi-dimensional NMR to separate these signals into multiple dimensions, so that we will be able to resolve them and find the chemical shift. Because what we see in the organic part itself, if you understand the chemical shift, you should be able to figure out where in the molecule these particular resonance originate from, right? Similar way, we have to identify each of the signal. Where is it originating from, right? How do we do that? We have to do multi-dimensional NMR. I'm not going to talk to you about multi-dimensional NMR, but it's possible to do it. If anybody wishes to know it further, we will have to have another 2.5 hour lecture. Yeah. So I'll just tell you about how we do protein NMR. Okay, the first thing is sample preparation. That means mainly molecular biology work. And then we do NMR spectroscopy, where you view multidimensional NMR spectrum in order to assign these. Assign meaning to figure out the chemical shifts and to assign the peaks to the amino acids. Okay. Then finally, structure calculation using computer. Right. So how do we do that? What we need is a protein of interest and the DNA sequence of that. Then we clone this into a vector and then use a suitable plasmid and recombine. We reconstitute them and then put it into a bacterial cell and make it express the protein. Okay. Now this is so the bacterial cell will express the protein. Now what we do generally, this is where. It's a flask where the bacteria is sitting there, and you see small little stuff there. That is bacteria colonies, and they are making your protein. Now there is also a liquid there. These liquids are the food for the bacteria, mainly the growth medium. And this growth medium contains. Normally, what we do is we need to. Since we want to do multidimensional NMR, we replace all the carbon 12 of your proteins with carbon 13 and all the nitrogen 14 of your protein with 15N. So how are we going to do that? We in the growth medium, we supply 15N ammonium chloride and carbon 13 glucose. Okay, so this the bacteria incorporates into the protein. So their only source of food is glucose, which is carbon 13 labeled, and ammonium, the nitrogen source will be ammonium chloride, which is 15N labeled. So 15N ammonium chloride and carbon 13 glucose is being taken in by the bacteria and expressed. When they express the protein will have carbon 13 and 15N incorporated. Okay, so that when you're done, then you kill the bacteria, purify, and then we get the protein. Now we can do what is called an HSQC. This is an HSQC of your protein and protein molecule. And what you see, these dots are NH correlation. NH, nitrogen in this direction, and proton in this direction. Okay, NH correlation. Okay, each of these NH will correspond to one amino acid. You know that how an amino acid, right? You have NH, CO, the alpha, like that it goes. So this NH, this is the peptide bond, right? This is a peptide bond. So this NH, so each amino acid peptide bond will have a correlation. So if you see a correlation, that means there is a peptide bond, and that peptide bond is giving you that NH. So we have to understand from which amino acid this NH correlation corresponds to. These dots has to be named from the amino acid sequence, right? So this is like our connecting the dots. There are so many dots here, but we do not know which dot, where the naming, where the numbers are. What we, however, know is the amino acid sequence, primary sequence, how each amino acids are, which amino acid is consecutive to each other. That amino acid sequence numbers we know. Alanine is first, threonine is the last, and things like that. But we should be able to figure out from the sequencing of amino acid. Okay, so we have to now understand if this alanine, where this alanine is in your molecule, in the spectrum, where you have to identify the NH peak that corresponds to that alanine. Okay. However, there are two alanines. Okay, in your sequence, this is going from, this is a 76 amino acid protein called ubiquitin, and you see there is two alanines here. Okay, so we do not know which alanine, where this is in this one. So this is not only to identify the amino acid, it is also sequentially we have to identify. That means this particular alanine has a neighbor, two lysines as neighbors, right? While this particular alanine has a phenylalanine and a glycine as a neighbor. Okay, so it's able to identify. You have to be able to identify sequentially where the amino acids are. Okay, so that we have to do. We can all do this. We can do this using multiple NMR experiments. So in all of our discussion, I was talking about this particular single pulse experiment, 1D NMR, where you apply a 90-degree pulse and observe 90-degree pulse, and we see there is an FID. You see, these are all pulses. We create multiple pathways that can transfer magnetization from proton to nitrogen, nitrogen to carbonite, or nitrogen to carbon C alphas, and then back to proton. We can do all kinds of spin jugglerly, spin dance or spin dynamics with it. Okay, what we get information is the correlations, which amino acid is correlated to which amino acid. That information is what we get. Okay, so this is just not one single experiment. We have to have multiple experiments, and then it's like solving a puzzle. You know, we get a lot of peaks, and we have to solve this puzzle. Which is going with which amino acid is going with which peak has which peak as its neighbor, which coupling is its neighbor, and things like that. So it's a big puzzle we have to solve. Okay, computer helps, but normally it's done. Now, once we do that, we should be able to know each of these. For example, this particular peak, this NH correlation. You know, this is a ppm level of proton, and this is the ppm of 59, as I told you. This NH proton corresponds to glycine at 47 position. This particular peak corresponds to alanine at 46 position. Okay, so, and you see the second amino acid, this peak corresponds to alanine at 28 position, right? So these are possible way. This is how you assign the protein. Once you assign the protein, now what we need to know is to do the distance between these spins, because in a structure calculation, that is what is important. You know, when you see primary sequence is a sequence of amino acid. From like a linear way. But how do you know it's to find the secondary or tertiary structure, this sequence will fold up, right? Fold up into a nice looking protein structure, right? So how do we know that this guy is closer to this guy when it's folded? That means that we have to know distances between them. We have to understand distances between them. Okay, that we do by what we call NOEs. Okay, nuclear overhauser effect. So if you it's like a COSY experiment where if you see a cross peak between the two signals, like here and here, cross peak between 5 and 2, that means these 5 and 2 resonances are close to each other within 5 angstrom. Okay, that is what it tells you. Okay, so that is possible to do through NOE. So this is another set of experiments we have to do in order to find the distances. Once we find the distances, so we have labeled the amino acid. Okay, we have labeled the amino acid, but then this is like this. Now we find the distances, only then we know that this is actually a shape of fish, right? Otherwise we don't know whether it's a fish or it's something else. Huh? So we have to find the distances between these amino acids using NOC. And once we find the NOC, then we put everything to the structure calculation protocol, and we get 3D structures. Okay. This was completely fun, and then these are some of the structures we solved. And thank you very much for your attention. And if you have any questions, please, you should be able to. I think with this, you should be able to get a fairly good idea about solving the problems tomorrow also. Okay. Is there any questions? Hello?
Participants, kindly post your questions in the chat box if you have any.
There are some questions are there. I will answer them. Okay, Smita Mane again writes, sir, from where we get that integration number? So in the spectrum, when you actually measure when you display the spectrum, we can integrate. We can do integrate, and from the spectrometer itself, or from the computer itself, they find the integral value and then depict the integration. That will give you the integration number. Okay. Read like J can be negative also. How is it possible? Yeah, J can be negative. For example, nitrogen, it's because the gyromagnetic ratio of some of the molecule, as well as the as I told you, if the gyromagnetic ratio is different, then the polarizability there is always. I mean, if you remember my first, if you go and look at my here, if you see that I put the plus half down and minus half up. This is only true if your gyromagnetic ratio is actually positive. Okay, there are nuclei with a with negative gyromagnetic ratio. Okay, and in those, the minus half would be the lower energy state compared to plus half. Okay, and so if you have couplings like that between these two hydrogens and nitrogens and things like that, then you get a negative coupling also, because their polarizability is going to be different. Dr. Sarvana Kumar, how to correlate NMR using Gaussian software with experiment one? I'm sorry, Sarvana. Sarvana Kumar, I do not know how Gaussian software. Normally, chemical shifts, you get a fairly good idea, but you cannot completely rely to predict or calculate chemical shifts from experimental one, because that would be the most easiest thing to do, especially biomolecules and all. You do some calculation and you get a chemical shift. People have been trying to do it to represent accurately the experimental chemical shift with that of the measured. The problem with Gaussian or anything is that the normal chemical shift, when we measure chemical shift, this chemical shift or the chemical shift of a molecule depends also on the temperature. It depends on the solvent that you are using. So there's a lot of parameters, and Gaussian or any softwares will not be able to represent them fully. So therefore, it is not very accurate to directly compare measured chemical shift from the experimental one with that of especially a quantum mechanical calculation like Gaussian. Dr. Subin Kumar asked, can you give an idea about NMR spectrum other than 1H and 13C? There are, of course, 31P and 19F, fluorine NMR and phosphorus NMR. They are both spin half. The chemical shift, of course, are going to be different, but the idea still holds. Fluorine, of course, is the high electron negative atom, so but they can still show very good chemical shift differences. I do not know the exact range of these chemical shifts, but one can easily find out from Google and things like that. But the same idea holds. It's a spin half. It's very easy. For spin higher than half, like you take deuterium, you take boron and other stuff. Boron has two spins, 3/2 and 3, I think. So boron 11 is 3/2. So that is what we actually take normally measure. So they are going to be broad because of the quadrupolar coupling. Okay, quadrupolar coupling are quite heavy, and that is going to be very broad unless you get only sharp peaks if you have very good symmetry in your molecule. Okay, so that is a possibility. And I am only talking about solution NMR. There is, of course, solid state NMR, and that's a completely different thing. Normally, solid state NMR does mainly these quadrupolar spins. Is there VG? I probably answered the same thing. No, you were talking about HNMR. What are the significant others? There are these. Mainly for proton, especially organic molecule, one measures 31P and fluorine. If the molecule has fluorine and 31P. And normally measures 15N unless it's biological NMR or you enrich with enrich the nitrogen with 15N. Okay. There are no further. Did I miss any questions? Miss, I think.
Is there any more questions?
I think there are no further questions.
No further questions, sir.
Okay. I hope you got a good idea. If there are any questions, especially that Fourier transform, I cannot. Well, if I forgot his name, but if he wants, I can send an handout or something. Then if he has any doubt, he can directly contact me. My email ID, I just put it on the chat. And this is my phone number. This has WhatsApp if you.
Thank you, sir. Thank you very much. It is indeed a great privilege for me to propose vote of thanks to the speaker of the day, Dr. Vinesh Vijayan. On the behalf of organizing committee, Vishnu College, Mavelikara, I would like to thank Dr. Vinesh Vijayan for the excellent and informative session. The way he explained the topic was exemplary, from fundamentals to advanced, that is interpretation of spectra. I think all the participants were highly benefited by this informative session. Thank you once again, sir, for being with us. Thank you.
Thank you for inviting me.
Thank you, Dr. Vinesh, for your useful session. It's a very excellent and very informative session. Thank you, Dr. Abha, for providing chairing the session. Dear participants, we are extremely apologizing for the technical issues we met today. So we are contacting G Suite and try to find out a solution for the same. We hope by today itself we can solve the problem. If the problem still exists, we try to find out another solution and will inform the same for through the Telegram group and also through your email. So please check your Telegram and mail. Then tomorrow is our final day of our FDP. For tomorrow, there is one technical session by Dr. Viman at 10 to 11:30, and the valedictory function will start at 11:30. Definitely, we will provide today's recording soon, and we provided the feedback link in the chat box, and it also shared through the Telegram group, and also it is emailed to your email account. So once again, we really apologizing the technical errors we met today. Thank you once again. Thank you, Vinesh sir, for your fruitful session. Thank you all.
Can I log out?
Okay,